Math 3414, Week 11, Video 3, Post-ANOVA Analysis, Estimating the Difference in Two Population Means. In addition to just estimating a single means value like we did in the previous video, we can also pick two populations and try to estimate the difference in their means. I want to remind you that when we come up with this estimate, there's one of three things that can happen. Specifically, and we'll get down to the steps in just a second, when you're estimating mu1 minus mu2, and you get an interval from one number to another, if both numbers are positive, that means that we're confident that that difference is positive, which means that we're confident that the first mean is greater than the second. But if that difference were negative, if the interval contained two negative numbers, then we're confident that that difference is less than 0, aka negative, which means we're confident that the first population mean is less than the second. The only way the subtraction problem could be negative is if the first number were smaller than the second. But if our interval starts with a negative number and ends with a positive number, that means it must contain 0. That means that maybe the difference is equal to 0, which is the same as saying the means are equal. That's an equal sign. So when we estimate the difference in two values, we come up with one of three conclusions. If the interval is completely positive, then we can estimate, or we can state confidently that the first value is larger. When the interval comes out completely negative, then we are pretty confident that the second value is larger. But if the interval starts negative and ends positive, that means it contains the number 0, which means it's possible that the two values are equal to each other. So we'll make that an analysis once we actually do this particular confidence interval. So how do we estimate the difference in two population means post-ANOVA style? Well, like any other confidence interval, it's got the same four steps. Find the Z or T, which in this case is the T. Find the standard error, find the margin of error, and then calculate the interval. As far as the first step, find the T, it's exactly the same as it was in the previous video. The T distribution requires degrees of freedom, and for this interval, the degrees of freedom is the same as it was before. It's n minus k, which is also the degrees of freedom of errors in your ANOVA table. The standard error formula, however, is a little bit more convoluted. It's not that much more convoluted. Recall that on the previous video, now this is not the formula, this is the one from the previous video. It was the square root of MSE over the square root of NI, whichever population sample you're looking at. But that's when we were estimating a single population mean. To estimate the difference in two population means, it's going to be a long, tall square root. And under the square root, we immediately start with MSE. And then after that, we have some open parentheses where we have the sum of the reciprocal, so 1 over the two sample sizes from the two populations whose difference in means we're estimating. So we'll say NI and NJ. Again, two populations means two samples, which means two sample sizes. It's not a difficult formula to set up, but if you're not careful, you can put it in your calculator incorrectly. Margin of error, not really much to discuss there. As usual, it's the product of the first and second results. And then for our interval, your interval is always centered at the sample version of the population value that you're estimating. We are estimating the difference in two population means, which means we're estimating something like mu I minus mu j, whatever those two numbers represent. I need a better stylus. This one's kind of giving out on me. Try this one. So we're estimating mu I minus mu j. So when we set up our interval, we have to center it around the sample version of that, and the sample version of mu is x bar. So our interval is going to be centered around x bar I minus x bar j. And again, the I or j are just numbers that are generic, referring to two of the populations involved in the ANOVA, plus or minus the margin of error. So just like the previous one, and just like all other confidence intervals, it's the same four steps. You just have to adjust the distribution that you use and adjust the formula for the standard error. And when you build your interval, make sure you center it around the correct point estimate. All right, so let's do this. But in order to do this, we have to pick two populations to estimate the difference in their means. So let's take a look at the Excel document that currently has all of the information. And I am going to undo all the highlighting that I did from the previous video. Oh, okay, there we go. And rename these ATM1, ATM2, ATM3. Recall that in the previous video, and hopefully you watched it, we built an interval around this guy. We estimated the population mean for the third ATM usage, and that interval excluded both of these values. So in the previous video, we had pretty good evidence that the third population's mean was different than the other two population means. But what about these two? Are they different enough? Well, let's find out by building a confidence interval estimating the difference in their population means. All right, I'll be going back and forth between the spreadsheet and the whiteboard. Okay, so let's estimate the difference in the mean usage for ATM1 and ATM2. Use 99% confidence. All right, so what's our first move? Well, the first move is the same as it's always been. Our first move is to calculate Z or T. In this particular situation, it's going to be T. We're going to find T. Our degrees of freedom was N minus K, or DF errors, whichever way you want to think about it. So in this one, let's just remind ourselves where it was, since we don't want to assume everybody's watched the previous video, but you should have, especially if you're in my class. Where is N and K? N is the grand sample size, so it would be the sum of all the samples sizes. So it would be 24. And K is the number of groups. There are 3 groups. So 24 minus 3 is 21. Or you could just look in DF errors right there. So no matter how you slice it, the degrees of freedom is still going to be 21, as it was in the previous video. Come on. Sorry, I'm having sharing issues here. There we go. All right, so our degrees of freedom is going to be 21, just like it was before. It just dawned on, oh, excuse me, I was going to say it dawned on me I didn't give a confidence level. I did, 99% confidence. So let's draw the bell curve associated with this. Confidence level represents the middle area of a bell curve. Since we're using T, we're going to find the right tail area because that's what our T chart tells us. If 99% is in the middle, that means that there's 1% for the two tails together. So half of 1% is a half percent. We have 0.5% in each tail. So be very careful when you're looking this up in the T chart, because you want to look it up as a decimal by moving the current decimal 2 places to the left. And you get 0.005 as the area in that T chart. So degrees of freedom 21, 0.005 in the right tail. Let's go to our T chart. All right, so 0.005 is way over here. If you look in the second column, you're doomed. 21 degrees of freedom. So we're in the second to the right column. 21 degrees of freedom is here. Looks like our T score is 2.8314. 2.8314. All right, so there's our first piece of the puzzle. What's our second step in a confidence interval? By the way, when we reviewed all that at the beginning of the semester, I wasn't kidding when I said it's going to come back again. Our second step is to find the standard error, and that's just a formula. So let's break out the formula. For standard error is the square root of MSE times 1 over the first sample size. Now, one thing we haven't really set up yet, and maybe we should have done that at the beginning, is what order are we estimating the subtraction problem in? If we're looking at the difference in the mean usage for ATM1 and ATM2, then it's reasonable to say that we're going to estimate mu1 minus mu2. But honestly, it could be mu2 minus mu1. It really doesn't matter what order you set up the subtraction problem, as long as you're consistent with what you call first and second. So we'll say all the ATM1 stuff is first and all the ATM2 stuff is second. That makes sense. All right, so anyway, our two sample size are two same populations of the first and second, and so in the formula for MSE, it's going to be 1 over the first sample size plus 1 over the second sample size inside those parentheses. Well, we have all these values, we just have to go get them from our tables. So where is MSE? Well, MSE is in the same place it was before, it's right there. 138.7143. And while we're at it, our two sample sizes are both 8. That's pretty easy to remember. 138.7143. 138.7143 times 1 over the first sample size plus 1 over the second sample size. And again, this can be a calculator issue, so I strongly recommend getting out a calculator right now and putting this inside your calculator. See what you get. And I just had some leftover stuff from a previous calculation. So let me clear out my calculator. Let's see. To 4 decimal places, I got 5.8889. Might want to put it in your calculator to make sure that that's what you get. In case you're wondering what I'm doing, my laptop is telling me, hey, I'm low on power, so I'm just going to plug it up real quick. And again, at this point, you should be putting that in your calculator to make sure you get the same answer. And I'm going to do it also, again, just to make sure I don't make a mistake. Yeah. All right, so let's try this again. By the way, when I put things in calculators, I know some more efficient ways to put things in calculators, depending upon the problem. So I will usually put these problems in different orders just to make sure I get the same answer, but I did. I got 5.8889 if you round it to 4 decimal places. All right, so there's our standard error, and at this point we're practically home free because now we just have to calculate the margin of error and the actual interval itself. We'll go ahead and set up the margin of error here. Margin of error is going to be our t-value, which was 2.8314. Yes, 2.8314 times our standard error, which was 5.8889. And again, we're just going to stick with the convention of rounding each answer to 4 decimal places as necessary. This keeps things from getting unnecessarily out of control. To 4 decimal places, I get 16.6738. It's actually a pretty large margin of error. All right. I don't feel like I would mistype this one, but it doesn't matter how good you are. Don't be so cocky to think that you can't make mistakes. I got the same answer again, so either I made the same mistake twice or it's correct. All right, so there's our margin of error. And now all we have to do is find the interval. Let's go back to the text box. And because we're about to run into the work for the standard error, let's just go really low to get out of the way there. All right, so find the interval. Type that there and we'll draw the rest. All right, so for the interval, we have to take the sample version of what we're estimating. We're estimating mu1 minus mu2, and so the sample version of that is x bar 1 minus x bar 2. Then add or subtract the margin of error. Now, my advice when you're doing a confidence interval for estimating the difference of things is to calculate the difference first and then stick the margin of error on it, margin of error being 5.8889. No, that is not correct. In the wrong place, margin of error is 16.6738. But in what I call a thought cloud, this is what you're thinking here. I need to subtract my 2 sample means, which means we need to go get our 2 sample means, which are contained in the spreadsheet. Our 2 sample means were right here, and we are doing first minus second. So it will be 30.75 minus 4. 30.75 minus 4. Minus 34, excuse me. And that should be negative 3.25. And we will move that into the confidence interval setup. Spidey senses are tingling. Nope, negative 3.25 is correct. Never mind. All right, so what is this? Well, This is just a matter of doing the math. Negative 3.25 minus 16.6738 is negative 19.9238. And if we do the addition problem, negative 3.25 plus 16.6738 is 13.4238. And there is our interval. We're estimating the difference in the two mean usages of the two different ATMs. But we're not just going to get the answer, we're going to figure out what it means. Because remember, at the end of an ANOVA test, if you said at least two population means are different, you're looking for evidence to suggest that that might happen. But notice that this interval starts negative and ends positive. Let me go back to it real quick. That this interval starts negative and ends positive. Any such interval must contain the number 0. So we can draw a conclusion as follows. Since the estimate for, and I'm just going to say mu1 minus mu2, and I should say the interval estimate, as opposed to a single value, which would be just the difference in the x bars. Since the interval estimate for mu1 minus mu2 contains 0, it is possible that the population means are equal because it's possible that the difference is 0. So in other words, do not have sufficient evidence to conclude that ATM1 and ATMU are used differently on a daily basis, since we were looking at daily averages. Had the interval been completely negative, let's just go back for a second. Had the interval been completely negative, starting negative, ended negative, then we would be confident that this difference is negative, which means we would be confident that the second mu was greater than the first mu. But if the interval had been completely positive, then we'd be confident that that difference is positive, so we would be confident that the first mu was greater than the second mu. All right. So that's estimating the difference in two population means post-ANOVA style.